Hi guys, this is a P3 replay for the Resonance Beyond Pi delocalization or non-traditional resonance lesson, and it was pretty tough, but it asked you to invoke quite a few concepts and use quite a bit of information that's given in the question. So I'll go through the process here of sort of logically how you can glean from the question's information and from what you know about non-traditional resonance FMOs to solve this problem. So in this problem we're interested in conformation B of this sulfoxide, which places the lone pair that you see here in the plane of the molecule, right? So in the plane of the double bond. The oxygen and the CH3 are above and below the plane, respectively. The energy values that you see in table 3 or figure 3 are the stabilization afforded by a particular interaction. So, for instance, the pi bond delocalizing into the sigma star of the SC bond right here is worth 1.7 kilocalories per mole. Now the question asks us to draw the resonance contributor for conformation B that involves the most important sigma bond acceptor, and to draw curved arrows to show that. So the most important thing really is to identify, okay, what are the structural elements in conformation B that are going to be involved in the most important resonance interaction involving the most important sigma bond acceptor. So a common mistake was for people to see 2.4 and immediately start thinking about the N to pi star interaction involving the sulfur's lone pair and the pi bond. There are two reasons why this is incorrect for conformation B. One is that the lone pair is in the plane of the molecule. So the pi star orbitals, which are above and below the plane, cannot actually interact with the lone pair, which is in the plane and perpendicular to the pi star orbital. The other is that the acceptor is not a sigma star, but a pi star. Because the problem tells us that we're looking for a sigma bond acceptor, we need to think about a sigma star getting involved and not a pi star. So we can rule out the bottom three entries in figure 3 as possible resonance interactions here. What we can see from the first two is that the sigma star of the SO bond is the orbital that's most likely going to get involved as the acceptor. I know that because 1.9 is greater than 1.7, and the stabilization due to that interaction is greater than the stabilization by delocalizing into the sigma star SC. So with this information in hand, we can then take the pi to sigma star SO interaction, basically make that happen in curved arrows. And we can do it by just simply looking at the interaction and thinking about how the curved arrows will proceed. So starting at the pi molecular orbital, we're going to start with the double bond. In order to make those electrons interact with the sigma star of the SO, we'll move them into a new double bond and kick electrons up to oxygen. These are the curved arrows implied by that interaction. And in this particular problem, it was important just to apply those curved arrows very liberally, right? Treat them extremely literally, and don't worry too much about the charges you're creating and things like that. What you might be surprised to find is that in the corresponding resonance structure, the resulting resonance structure, we actually place a 2- charge on oxygen as a result of our curved arrows. So just following my directions from before, moving the pi bond over, that leaves a positive charge here on the carbon, breaking the SO bond and making O 2- now. Believe it or not, this resonance structure with the O2- is the most favorable resonance structure involving a sigma bond acceptor.